Welcome again to Quadranscentennial KIAS Lecture by Professor Birkar. So in this second lecture, he will speak on boundedness and moduli of algebraic varieties. Okay, please.
Okay, thank you again for the introduction. In this second talk, I'll talk about boundedness and moduli of algebraic varieties. This is a natural continuation of the first talk. In the first talk, I tried to explain that if you have any algebraic variety, then birationally we can transform it so that in the end, we get a variety with a kind of special property that either you have a Fano vibration, a Calabi-Yau vibration, or you have positivity everywhere. So it's natural then to try to classify this kind of special outcomes, not just an arbitrary algebraic variety. And that's where this talk, second talk is about basically these outcomes, but not all the outcomes, but these special classes that I defined in the previous lecture, Fanos, Calabi-Yaus, and canonically polarized. Okay, I will start with boundedness. Suppose that we have P, a set of projective varieties, or you can also allow schemes. We say that this set, this class, is bounded if we can find a projective morphism, let's say from V to T, where this V and T are schemes. They are a finite type, so that means that their dimension in particular are finite. And such that if you pick any element of your class of the set P, then this element, this variety or scheme, appears as a fiber of this given morphism over some closed point. So in other words, we have a kind of fibration V over T such that all the elements of P, they appear as fibers of this fibration. So the main point here is that these are finite dimensional, so that we can, in a way, this T parameterizes all the elements of P, but maybe much more. So it's not a one-to-one correspondence kind of situation. Let me just give you some examples of this phenomenon. If we look at all the hypersurfaces inside Pn, these are defined by one equation, homogeneous equation, let's say of degree less than or equal to R. So the R here is fixed. Then all such hypersurfaces form a bounded family. They will be bounded. They just follow from the fact that the degree is bounded and also that this Pn is fixed. More generally, if we look at all the subvarieties X inside Pn of, again, of degree at most R, where this time we define the degree of the subvariety X to be, first we take a hyperplane H. This is degree 1 inside Pn. We intersect it with X and we take the top intersection number. This will give you a number for X. This is the degree of X. Then we are assuming that this degree is bounded by R. Then the set of all such X, again, will be a bounded set, a bounded family. The third example, if we fix number G, then all the smooth projective curves X of the same genus form a bounded family. We saw this already in the previous lecture. So if P is bounded, if the set of varieties is bounded, then this implies that there is some two natural numbers, N and R, such that every X in our bounded set can be embedded into Pn with degree at most R. In fact, you can take this as another way of defining a bounded set. So bounded, either you define it in terms of fibrations or in terms of fixing an ambient projective space and then fixing or bounding the degree of subvarieties embedded into this Pn. You can also define it, refine it a little bit more by saying all the equations defining this X will be bounded by some degree and so on. So this gives you two ways of defining boundedness. Now, why bounded sets are important in algebraic geometry. Well, here I give you a few reasons. One reason is that if you have a bounded set of algebraic varieties or scheme, then their invariants, especially their numerical invariants, are also bounded. And in particular, so if you have something numerical, it belongs usually to a finite set. For instance, if you have a bounded set P, then the dimension of all the elements will be bounded. Moreover, the Hilbert polynomial, so this should be defined with respect to some embedding into some projective space, then this Hilbert polynomial can take only finitely many possibilities. And you can read many information about your variety or scheme from the Hilbert polynomial. And if we take X to be smooth, if we have a bounded set of smooth projective varieties, then their topological data also will be bounded. In particular, the Betti numbers with cohomology with coefficients in C, and also their Hodge numbers will be bounded. So they will be in some finite set, depending only on this class, this set P. So that's one reason why bounded sets are important. Another reason is that bounded classes, bounded collections of varieties help you to classify algebraic varieties, because that's, if you have, let's say, a very large class of algebraic varieties, then what you could do is to break it into parts and say that each part is bounded. So about each part, you have kind of better information, and then you say that, so, okay, if you understand all these parts, then essentially you are understanding the whole thing. So in a way, it helps you to classify algebraic varieties. For example, in the case of curves, fixing the genus then gives you bounded sets of algebraic curves. Another reason for boundedness being important is that it quite frequently helps to prove a general statement about algebraic varieties. So just as an example, if we look at all the X Fano variety of a fixed dimension D and with good singularities, here good means KLP singularities. Later, if I have time, I will define this thing, but for the moment, this is just some type of singularities. So if we fix the dimension D, only the dimension, then we can find a natural number M such that for every Fano variety of dimension D with this kind of singularities, then minus M times K, we know that it has global sections. So this is a boundedness kind of statement, although it doesn't say that X itself is bounded. But in order to prove this statement, we can use boundedness, at least of some parts of all such X. So essentially what we do is we divide it into two parts. One part we can prove the statement basically directly. The other part that we can't do, we show that they are actually bounded. And if they are bounded, then you immediately get this M. So boundedness can help to prove results in algebraic geometry. Also, maybe perhaps the most important reason for boundedness is that it's the first step of construction of moduli spaces. Because in algebraic geometry, we want moduli spaces to be projective, in particular a finite time. And for that, you need to show that your objects belong to a finite, to a bounded family. So that's why this is important for construction of moduli spaces. Also, if you have a bounded set of varieties or schemes, then when you are given a morphism, a fibration where the fibers belong to this set, then you are more likely to have a better understanding of this kind of fibrations, this kind of morphisms. Okay, so that's a few reasons of why boundedness is important. And now let me give you some examples of non-bounded classes of varieties. If we take P2, this is a projective plane. If you blow up this P2, let's say in one point, then all the possible surfaces that you get will belong to a bounded family. But if we blow up many points, not a fixed number of points, but arbitrary number of points, then the surfaces that we get will not be bounded. for easy reasons. Another class of non-bounded varieties is looking at all the smooth toric surfaces. So they are all birational to P2, but their number is just huge and they don't form a bounded family. Another example is all the K3 surfaces. Although topologically they are actually bounded, but algebraically they are not bounded. This form an infinite family. And also another example is all the surfaces, smooth surfaces with K ample, or all the singular Fano surfaces. So these are all two-dimensional, and if you go to dimension 3 and more, you can get a lot more examples. So already in dimension 2, we have a lot of non-bounded but important and interesting classes of varieties. Now, next I give you some examples of bounded classes of varieties, although these are not like concrete examples, but well-defined classes which are important for moduli. The first example generalizes the fact that if you fix the genus of curves, then all the curves with that particular genus form a bounded family. Now, in higher dimension, this is formulated in a different way. It is a result of Haken, McKenna, and Shrew, which says that if we fix a number, natural number d, and a positive, it should be positive rational number. And then if we look at all the projective varieties x with log canonical singularities. So this is another more general type of singularities such that this x has dimension fixed d, kx is ample, so in other words, x is canonically polarized, and the volume of this x is fixed. Volume, we can define it in terms of intersection numbers. This is kx to the power d is exactly this v. So we are fixing d, dimension, and value. Then the set of all such x form a bounded family. So this is related to moduli of, this is an important ingredient of moduli of varieties of general type or canonically polarized. And for Fano varieties, we have another result which says that if we fix the dimension d and we fix also a positive rational number, then the set of all the Fano varieties x of that fixed dimension and with good singularities, more precisely epsilon log canonical, this is another type of singularity, then the set of all such x belong, they form a bounded family. So this is also this is important for many reasons, but also in particular for moduli, for construction of moduli of, for example, Fano varieties, and also related to Calabi-Yau. And the final example is, again, if we fix the dimension d and v, here a positive rational number, then the set of all the Calabi-Yau varieties x with KLT singularities of dimension d fixed. And then if we take an ample divisor a on this Calabi-Yau variety x such that the volume of this ample divisor is exactly v, then the set of all such Fano or all such Calabi-Yau varieties x form a bounded family. And also we get some kind of boundedness for this divisor itself also in some sense. So in the case of general type, k will give you something ample. In the case of Fanos, minus k give you something ample. But in the case of Calabi-Yau, there is no natural ampleness around. So that's why we have to pick some ample device. Okay, so these are important classes of bounded varieties. And then I can talk about moduli. Suppose that we take P to be a set of varieties or schemes, and here usually means projective. A moduli space for the set P is a space that parameterizes the elements of P. And also it gives information about families of elements of P. This, of course, is not a precise definition, but the intuition behind what a moduli space is. So as you see from here, we have two parts. One thing is that we need a space to parameterize the elements of P, and we want that essentially to be in a one-to-one correspondence. So each element of P should be corresponding to exactly one point in the parameter space. And also, if you have a family where the fibers, if you have a fibration where all the fibers come from the elements inside this class, then we should understand something. We should get some information about this family. That moduli space should tell something about the family. Now, in general, when we try to define a moduli problem, then we need to keep in mind two important points. One is that we should make it clear, first of all, how we are looking at viewing the elements of P. Are we looking at them up to isomorphism, or are we looking at them up to isomorphism in some space? Or so there are different ways of looking at the elements of P. For example, if we look at curves inside P2, one way to look at all these curves is just up to isomorphism and ignoring the fact that they live inside P2. But another way is to look at them as curves embedded into P2. So in that case, even, for example, you can have two lines. If they are not the same line, then we can consider them as different elements inside the moduli. But if we ignore the embedding, then any two lines that you take inside P2, they are isomorphic. So they should correspond to the same point in the modular space. So you have to make it clear what you are trying to classify. And then the second thing is that what kind of families of elements of our class are allowed. So usually arbitrary families are not allowed. We need to make some choices to say that we only consider this specific type of families and we ignore the rest. So we have to keep these 2 points in mind when we try to define a moduli space, a moduli problem, and construct moduli spaces. As an example, let's look at hypersurfaces. So here, P is the set of all the hypersurfaces of a fixed degree R inside a fixed n-dimensional projective space. So here by hypersurface, I mean all the closed subschemes inside P and defined by degree R homogeneous polynomial. So they are not, strictly speaking, they are not all varieties in the sense that they may not be irreducible, they may have non-reduced structure and so on. So it's better to allow these things in this particular example. Then we see that there is a one-to-one correspondence between elements of this set and elements of the following set, which are the non-zero degree R homogeneous polynomials inside this polynomial ring, Ct0 to Tn, up to scaling by elements of C minus 0. So in other words, if we have a polynomial which is a scalar multiple of another polynomial, we just identify them because they define exactly the same subscheme. And then it's not difficult to see that we can parameterize all such polynomials. In fact, they will be just closed points. There will be points inside this new projective space that can be, its dimension can be calculated in terms of n and r. It's just simply because any polynomial, homogeneous polynomial here is determined by its coefficients up to this scaling. And so that will give you a point with, so the point will have the same coordinates as the coefficients of the polynomial. And therefore, the set here is parameterized by a nice space, which in this case is just a projective space. So itself is an algebraic varieties. It's a geometric space. So this is an easy kind of example, although this only gives you the parameterizing space. I didn't say anything about families, but let's leave that for the moment. We can maybe see in the next example. Now the next example generalizes this hypersurface example to something much more general. And then we get Hilbert schemes. Here, suppose that Y is a projective scheme phi is the polynomial over q in one variable, and a or h is a very ample divisor on this y. Then I take my set P to be all the closed subschemes X inside Y. So this Y in practice, you can take it to be the projective space. So here I have something more general, but you can think about Y as just being the Pn. Then we look at all the closed subschemes X inside this ambient space such that the Hilbert polynomial of X, so this should be defined with respect to this divisor here. This is exactly equal to my fixed polynomial phi. So we can define the Hilbert polynomial more precisely in this form. Is the Euler characteristic of when you restrict m times h to this subscheme X. These Euler characteristics give you a number, and that's the value of the polynomial inside with respect to this number m. Now, Grothendieck showed that that there is a projective scheme, let's call it h phi, the Hilbert scheme of this polynomial, such that well, I mean, this also depends on y, so strictly speaking, should also put a y, such that the elements of P correspond in a one-to-one way to the closed points of this Hilbert scheme H phi. Moreover, so that's the first part, which gives you parameterization of the elements of P, but we have much more. Say that, moreover, there is a universal family defined over this Hilbert scheme. So in other words, we have a fibration where all the fibers actually belong to this P. And we have something even stronger in the sense that if we take any other scheme S, and if we take any family that is given with that is parameterized by this S, so to be more precise, if we take any closed subscheme inside the product of Y and S, so Y is fixed, S now here is basically arbitrary, which is flat over S, and such that the fiber over any point little s has exactly Hilbert polynomial phi, then we get a commutative diagram like this. So very roughly speaking, this say that if you have any other scheme S, and if you have any family over this S, so the fibers will belong to P, then the statement say that there is a diagram of this form. I have my Hilbert scheme. This is the universal family over the Hilbert scheme. Then it says that there is a morphism from S to this Hilbert scheme, such that my given family should be just the pullback of the family, which is the universal family here. So in other words, this is saying that every possible family of my elements over any arbitrary scheme, let's say defined over C, it must come from this universal family in a unique way. And that's why this is a very important result in algebraic geometry, because it not only gives you a space which parameterizes the elements of P, but also gives you precise information about all families of my elements over essentially arbitrary base spaces. And in a way, this is like the best possible kind of a scenario that you can have in moduli, and that's why we call this Hilbert scheme a fine moduli space for our class P. So this is essentially classical example, and one of the most important examples of moduli spaces, because these days most other, or at least many other moduli spaces are actually constructed using this Hilbert scheme. Hopefully I come to this point in my talk. Okay, so let's now look at another example, the case of curves of fixed genus G, where for now I take G to be any number, non-negative number. Then, as I mentioned in the previous lecture, the set of all the smooth projective curves of genus G up to isomorphism, this is actually bounded, and it is parameterized The set is parameterized by the points of some variety mg. When g is equal to 0, then this space has only one point because we have only one curve of genus 0. If the genus is 1, then there is a one-to-one correspondence between the set of curves of genus 1, in other words, elliptic curves, with the points of the affine line, A1, and this is given by the Ji invariance. So you take any elliptic curve, you can associate a number to it, a complex number called the Ji invariant, and that will give you a point inside A1. So these elliptic curves are parameterized by just the points of the affine line. And for higher genus, as we saw in the previous lecture, you get a space of dimension 3g minus 3. Now, Deligne and Mumford, they say that we can actually compactify these Riemann moduli spaces Mg in a meaningful way, at least when G is more than or equal to 2. And for this, they enlarged this set of curves of genus G. They enlarged it so that they include now more curves which are not necessarily smooth. So I denote this by PG bar, and this is the set of stable nodal curves of genus G. Again, here everything is up to isomorphism. They say that there is a one-to-one correspondence between the set of the elements in this set and the points of some varieties Mg bar. This Mg bar is an enlargement of Mg. So Mg is embedded into Mg bar as an open set. Here, a stable nodal curve, I can define and also give you some examples of stable nodal curve of genus G. G is a connected projective curve X. This is a reduced, but it may have several components, such that X itself has only nodal singularities. So these are the simplest type of singularities, which also appeared in the previous lecture. And the genus of this X is equal to G. Now here we don't define this topologically as in the smooth case, but we use arithmetic genus. We just take H1 of OX to be equal to G. And for each rational component C of X, its normalization contains at least 3 points of the inverse image of the singular locus of X, where this pi here is the normalization of X. So it's much better. If you know these things, of course, you already know. If not, examples are much easier than this formal definition. So here are some examples of curves, stable curves of genus, a certain genus. The first example is simply smooth curves of genus G. Smooth projective curves, they are stable curves. So they satisfy all these assumptions. In another example, we can take, you could have 2 components that intersect at one point, intersect transversally, that means in the best possible way. And then one component, for example, can have genus 1, the other component can have genus, a different genus less than G, but they together can give you something of genus G. So you need to take into account the genus of each component and how they intersect to calculate the genus of the whole thing. In another example, we can have a smooth component intersecting another component, which itself is not smooth, but it has a nodal singularity. So for example, this could be the curve that appeared in my previous lecture, which was given by something like y squared minus x to the 3, at least in the affine plane. So this can be like a rational curve, although its genus now is not 0. It will be more than 0, but together with a smooth curve, it can give you a stable curve. So stable nodal curves they are all of this form, but such that you just have to be careful with only not the singularities, but also the rational components. So for example, in this example, the second one, if one of them is a rational curve, then this is not stable. if you want to have a rational curve in this picture, then it should intersect, either should have self-intersection like this. So this can be a rational curve, or if it has no self-intersection, then it must have at least 3 intersections with the other components. Then you get something stable. In fact, these conditions are here to ensure that the canonical divisor or canonical bundle of X, although X is not smooth, but still you can define canonical bundle. We want this canonical bundle to be ample. And that's why we put all these conditions. Now, why this kind of compactification is important? Because the points which are outside MG, they parameterize the stable curve, which are not smooth, but still they correspond to something which is geometrically understandable, not something arbitrary. So this kind of stable curves are not difficult to understand in the sense although they are not smooth, but in many ways they all kind of behave like just smooth curves. Okay, and then, so that was the moduli for the case G more than or equal to 2. But when you look at moduli of curves of genus 0 or 1, the story is a little bit more complicated. So I think I will not have that much time maybe to go into all the details, but let me just go through this quickly. Let's say we are interested in the moduli of curves of genus 0. Let's call this set P0. Of course, we know that we have only one curve of genus 0, which is P1. So if we have a moduli space, then it should have only one point, because we have only one variety to parameterize. Although this one point parameterizes the set, but it's actually not a perfect kind of moduli space for our set. The reason is that when you look at families, then you see that something strange can happen. And by that, I mean that if you, for example, look at a ruled surface, a ruled surface is a P1 bundle of a smooth curve, then you can take this ruled surface to be not isomorphic to P1 times the base S. There are plenty of examples. For example, you can start with S and then some vector bundle on S, and then you can construct this kind of W. So in this case, a specific example is just take this vector bundle locally, free shift O plus O1, and then take its projective space. It will give you this kind of W. However, if I consider this ruled surface as the family over the base, all the fibers are P1. But if I have a moduli map from my base to the moduli space, then every point should go to the single point in the moduli space, because M0 has only one point. However, this is not a moduli space like in the case of Hilbert schemes. It's not a fine, or let's say, informally call it imperfect moduli space, because my family is not a pullback of any universal family. If there was a universal family, it would have only one fiber, which is P1. And if this was a pullback of that family, then this should be just a product. But I know that this is not a product. So this is not a fine moduli space, or in other words, it doesn't behave as good as the Hilbert scheme. We will see later that we can talk about coarse moduli spaces. Again, on P1, I can also add points and then look at moduli spaces and in fact construct moduli spaces. But since I don't have much time, let me skip this bit here and go to the definition of moduli functors. So far, when I talk about moduli spaces, except in the case of Hilbert scheme, the discussion was in particular for families, behavioral families was kind of vague and not very precise, but now I can make this precise. For that, we need to define moduli functors in order to formulate moduli problems. Moduli functors work as follows. You take SCH, this to be the category of schemes, let's say over C, and then you look at the category of sets. And then we want a functor, a contravariant functor from the category of schemes to the category of sets. Now, in practice, we can also replace the category of schemes with some subcategory, depending on the moduli problems. And then we say that this f as a functor is representable if there is an object, if there is a scheme M, such that this functor is given exactly by morphisms into this M. So in other words, the families that are given by this functor, they basically just give you morphisms from the base into this M. If we have this kind of situation, like in the case of Hilbert schemes, then we say that M is a fine moduli space, but quite often these kind of moduli spaces don't exist. For that reason, we need to define something weaker. This time again, I look at the category of schemes and a functor from the category of schemes to the category of sets. We say that this is coarsely represented or representable if there is a scheme M and if there is a natural transformation of functors from my given functor F to the functor which is home into this moduli space M, such that for points, by point I mean spaces that are just given by a field, spec of K, I want the functor, so all the families over this point given by the functor should just correspond to the maps from these points, spec of K, into my moduli space. So for example, if I take this K to be just a complex number, this is just simply saying that all the objects that are defined over a point must, so in other words, all the elements in my class must correspond in a one-to-one way to the points, to the closed points of the moduli space. And also in the definition, we need this universal property that if I have any other scheme N, and if I have any natural transformation from F into home given by this N, then I want this to decompose in a sense. It must be a unique way of defining a natural transformation from the home given by M to the home given by N, commuting with all this data that I have here. So this is a bit technical. Let's not worry so much about this thing. Essentially, this saying is that you need, when you have a functor, to have a coarse moduli space, you need a scheme. And then if you take any fibration, we can think of F as a fibration that you have. If you take any scheme, then F of that scheme gives you a family over families over that S. For any such family, we want to have a map from the base to the moduli space, where it sends a fiber to the point which parameterizes that fiber. So that's basically what it says, but there may be no universal family involved. And in practice, this P will be just a set of varieties or schemes, and then okay, let me skip these things. Also, let's just look at one example. This is just the Hilbert scheme example where I take an ambient space Y or the projective space Pn, and then A or H, some very ample divisor on this ambient space. I fix a Hilbert some polynomial over the rationals in one variable. Then P, as you remember, were closed subschemes of my ambient space with given Hilbert polynomial. And in this case, the functor gives you, for each scheme S, gives you essentially all the families in the definition that are defined over that particular base S. The next example is those of smooth projective curves of fixed genus, but since we have seen that already, so let me not spend much time on that. And next, what I want is to tell you what is the general strategy for construction of moduli spaces. This almost always appears when you try to construct moduli of some classes of varieties or schemes. So suppose that we start with a set P of projective varieties or schemes. And suppose that we have defined a moduli problem, which means more precisely that we have a moduli functor as in the previous definition from the category of schemes to the category of sets, or you could replace this by a smaller category of schemes. For example, it can be smooth varieties or normal varieties. First, suppose that we have shown that this P is bounded. So this is basically the first step. If we want to get an interesting moduli space in the sense of being a finite type, we need this boundedness to start with. So suppose that P is bounded. That by definition means that there is a projective morphism V to T. These V and T are finite types such that every element in P is isomorphic to the fiber of this fibration over some closed point. So in other words, I have some scheme T and a fibration over it where now all the elements of P appear as fibers, but maybe not in a one-to-one correspondence. So I can't call this T a parameterizing space or moduli space, but I can use it to construct a moduli space. In particular, this, as pointed out before, implies that there is some natural number n such that every x in this bounded set, it permits an embedding x into an embedding into Pn where n is fixed here, and such that the degree of x is bounded by some number. In particular, this implies that the set of possible Hilbert polynomials here are finite. And in fact, I can shrink my P and even assume that this is just fixed. Then, by Grothendieck's result, this means that every x inside my class determines a point inside the Hilbert scheme with respect to this polynomial and this Pn. However, this is not in a unique way. I mean, the same x can be embedded maybe, well, usually in many different ways. So if we look at the elements of P up to isomorphism, then this x can give you many different points inside the Hilbert scheme. So that means that the points inside the Hilbert scheme themselves, they don't give you the moduli space because they can't distinguish. They don't know that you have actually the same x coming to the same point. However, suppose that now that we have a locally closed set, and in the best possible case, suppose that we have a closed set, let's say R inside the Hilbert scheme, whose closed points are exactly those given by the elements of P. As I said, not in a one-to-one way. But if you are lucky enough, then maybe you can find a closed set like this, or at least something locally closed. This is usually the case, locally closed. And then what I can do now, if I want to construct a moduli space for elements P, I should somehow get rid of this issue that the same x can give me many different points inside the Hilbert scheme. That means that I need to define some kind of equivalence to say that if 2 points inside the Hilbert scheme come from the same x, then I should identify these points. I should collapse them to the same thing so that in the end I get a moduli space for P itself. And now the way that one x can give you 2 points inside the Hilbert scheme is up to an automorphism of the ambient space Pn. So if you have any x inside Pn, and if you take any automorphism, it will give you, unless the automorphism is identity, it will map your x to something else inside Pn. But in the sense of isomorphism, they are actually the same object. In an abstract sense, they are isomorphic schemes or varieties, but they just sit into different places inside Pn. As I said in the previous lecture, that if you have two lines inside P2, they are actually different. They give you different points inside the Hilbert scheme. They are not the same thing as embedded curves into P2, but in an abstract sense, any two lines are isomorphic. So they are actually the same thing. Therefore, this means that my set R, which parameterizes elements of X, I need to divide it by the automorphism group of Pn. And if I can do that, then this basically gives me the moduli space for my moduli problem. Now, if R is closed and if this quotient exists, then M is actually a compact moduli space. Now, in practice, it's much easier to construct this quotient as an algebraic space, not directly as an algebraic variety, not like a projective, quasi-projective scheme, but just consider it as an algebraic space. And then in the end, show that this algebraic space is actually a projective or quasi-projective scheme. So, I mean, if you want to do things directly to show that this is a scheme, let's say quasi-projective scheme, then usually you use a GIT. But this is problematic. What people do, I think this might be due to Euler, that you instead first construct the space as an algebraic space. So this is not necessarily a scheme. And then in the end show that you can actually find an ample divisor, ample line bundle on this space, and therefore automatically it becomes a projective or quasi-projective scheme. Okay, and now there isn't really time to go into definition of singularities, so I hope that you just take this intuitively. At least in the case of dimension 1, it's quite clear what kind of singularities we look at. Then I go now directly to moduli of stable pairs of general type. In this case, what we try to do here is to generalize the existence of moduli spaces of stable curves to higher dimensions. So this is a higher dimensional version of the same result, but this proof, all the ingredients that you need in order to prove this is way more than in the case of dimension 1, because this not only relies on the moduli theory itself, but also heavily relies on birational geometry to get many of the ingredients. So this is much more complicated. But anyway, let me just say a few words about this story. A stable pair, so this replaces a stable curve. This is a higher dimensional version. A stable pair of general type is a connected projective pair XB. Pair here means X itself is some kind of scheme similar to stable curves, not necessarily irreducible, and B is a divisor on it. And together they give you some kind of reasonable singularities, similar to the case of stable curves, but it's much more complicated in higher dimension, such that K plus B is ample. So if I remove the B, it just means that you have X with reasonable singularities and K ample. But it's actually better to work with pairs, not just X. So we have a pair. There are two conditions. One is local, which is about the singularities. Another is global, about positivity of this K plus B. So we need good singularities and positivity. And suppose that I fix several numbers, D, C, and V. D will be dimensions, C and V are related to coefficients and volume. And then I say that a DCV stable pair, this is of general type, XB is a stable pair as defined here such that the dimension of X is exactly D, the volume of K plus B is exactly V, and the coefficients of B are controlled by the C. In other words, I can say B itself is C times some integral divisor. So this is just about coefficients, this is about volume, this is about dimension. I need to fix design variance in order to ensure that my set is bounded and so that I can get a finite type moduli space. Now, a one-dimensional example of this kind of stable pairs are these, where here D is 1, C is half, V is 7/2. My X has two components. One component is a smooth rational curve. It has 2 points on it, each with coefficient 1. This gives you the B together with another point. The other component is also a rational curve, but it's a singular rational curve. It has one singularity. On it, also, I pick a point. These blue points are outside the singular locus. So X, Y, and Z together give me my boundary divisor B with these coefficients that are written here. This is 1, 1, and half. So we have X, we also have B, and then we can check that the singularities are reasonable. They are all nodal in this case. And we can also check that K plus B is actually ample. Now, in this particular one-dimensional example, that means something about genus of each component and the number of points and so on. But anyway, K plus B makes sense. You can look at its degree and you see that it is positive. So this is a stable pair of dimension 1. Now, so I defined stable pairs, but to define a modular problem, you also need to define stable families. In other words, you need to say that if you are given a scheme as arbitrary or something reasonable like normal varieties or smooth varieties, we need to say what stable families are. Now, very roughly speaking, without going into too much detail, a family, a stable family over a base essentially means you have a family where all the fibers of the family are stable pairs of the same type, DCV. Now, to make this actually work, to be precise, takes a lot more work, but let's pretend that it is not complicated. Then I have my stable objects and I have my stable families. Then I can define my moduli functor, which will be from the category of schemes or reduced schemes, depending on what you like, to the category of sets, where for each scheme S in my category, I look at all the DCV stable families. These are of general type over my base. This is defined over up to isomorphism over the base scheme S. Then work of many people, including Kohler, Alexeyev, and many other people, imply that there is a coarse and projective moduli space for this functor. So in other words, a higher dimensional version of Deligne-Mumford theorem holds. But the story, as I said, is much more complicated because you need, first of all, you need this whole machinery of birational geometry. Secondly, you need boundedness. This was, as I mentioned in the beginning of the talk, this was proved by Heiken, McKenna, and Zhu. And so this is basically a result of several decades, not just a few months. That's the general type case, and then I try to say a few words about the case of Calabi-Yau. So in dimension 1, if you take genus to be more than or equal to 2, then you are looking at general type situation. But if you take the genus to be equal to 1, then you are looking at the Calabi-Yau situation. Now in dimension 1, of course, it's maybe not so complicated, but when you go to already dimension 2, the problem becomes much more complicated. Now, here I define stable Calabi-Yau pairs. Projective pair XB with good singularities is called Calabi-Yau if K plus B is trivial. Let's just say numerically trivial. So you see that this is quite different from the general type case. In the general type case, K plus B is ample. In this case, K plus B is trivial. So this is the second class. If you remember from the previous lecture, I had three very important classes: Fanos, Calabi-Yaus, and general type or canonically polarized. So I already talked about the general type case. This is the case of Calabi-Yaus, and the case of Fanos also can be in a way embedded into this Calabi-Yau story. Okay, so this is just a Calabi-Yau, but I should then make it clear what I mean by stable Calabi-Yau. Well, suppose that I have an effective divisor A such that xb plus a small multiple of this divisor is stable. Here I write KSBA stable. It just means stable in the sense of general type. Then we say that xb, this pair together with the divisor, is a stable Calabi-Yau. So remember that I mentioned before, if you are given a Calabi-Yau, for example, an elliptic curve, there is no natural ample divisor on it. You have to make some choices. So we pick some ample divisor, and in this case, I want this ample divisor to be effective also. So this is not a choice of just a line bundle, but a divisor, an effective divisor, like a section of some line bundle. Then this gives me a stable Calabi-Yau. So stable Calabi-Yau is Calabi-Yau together with some effective ample divisor such that I have also some good behavior of singularities. This kind of stable Calabi-Yau pairs, it appears gradually in work of Alexeyev, Hassett, Hakin, and so on. So I'm almost at the end of the talk. There isn't really much time here to go into examples, but I just roll the slides so that hopefully later you can read. But let me just tell you at least the statement, the main statement about moduli of stable Calabi-Yau pairs. In this case, also we fixed three numbers, D, C, and V, and then we define D, C, V stable Calabi-Yau pairs. These are X, B, and A, which is stable according to our definition, and such that the dimension is fixed by D. Coefficients of B is given by this divisor, by this number, controlled by this number C, and A is volume. The volume of A is exactly equal to V. So here I'm pretending that A is an integral divisor, but you can also allow non-integral case. In that case, you have to similarly control the coefficients, like in the case of B. But here, let's just look at the integral case. Then I also can define a DCV stable family of Calabi-Yau pairs over base schemes S. In particular, the reduced case I usually deal with. And then finally, I can define a moduli functor from the category of, let's say, reduced scheme to the category of sets, where each base scheme S gives you the set of all the DCV stable families of Calabi-Yaus over this base scheme up to isomorphism. And then the main result here, which is just from last year, which says that with this given invariant, this data D and CV, then this moduli of stable Calabi-Yau pairs with this data actually exist, and it's a projective coarse moduli space. So it's a finite type moduli space. Okay, I will stop here.
Okay. Okay, thank you very much for your nice talk.
Okay, thank you so much, and thank you for listening.